a cooling cup of coffee, a collapsing star. From the smallest gesture to the grandest event in the cosmos, everything follows the same invisible law, a force that pushes time forward, gives rise to life, and ensures that one day, everything will come to an end. But what is really changing? And why can this change never be undone? Today, you'll uncover the hidden engine of the universe, the law that turns order into chaos, and chaos into everything we know. The universe has a direction. Even if we don't notice it, everything is moving from a state of order toward one of greater chaos. Glasses break, but never reassemble. Heat flows from a hot body to a cold one, never the other way around. And we age, but never grow young again. There's a law behind all of this. A law so powerful that it defines the flow of time, the course of life, and ultimately, the fate of the universe itself. That law is entropy. It's one of the simplest and most misunderstood ideas in physics. And it's not just about disorder, as many textbooks suggest. Entropy is, above all, the natural tendency of energy to spread out, to diffuse, to become less useful. It's why your coffee cools down, why air spreads evenly across a room, and why the sun will one day burn out. But it's also the reason you exist, because without entropy, without this constant transformation of concentrated energy into dispersed energy, life could never have begun. To understand entropy is to understand the story of the entire universe, why it started, how it evolves, and how it will end. And maybe it's also to understand what it means to be alive in this brief moment between the beginning and the end. In the early 19th century, the world was obsessed with machines. Steamships were crossing oceans, factories were rising at a frantic pace, and humanity seemed to have finally mastered the art of harnessing energy. But there was a problem. No one could explain why these machines wasted so much energy. That's when a young Frenchman named Sadi Carnot, the son of a Napoleonic general, decided to investigate the mystery. He wanted to know if it was possible to create a machine that could convert all heat into useful work with zero waste. A perfect machine. Carnot spent years studying steam engines and eventually made an observation that would change physics forever. No matter how well built a machine is, some energy will always escape. Part of the heat inevitably disperses and can never be recovered. It's the price of every transformation. He described an ideal engine, one without friction, where heat would flow between two sources, one hot, one cold. Even in this perfect scenario, Carnot showed that efficiency could never reach 100%. There would always be a gap between the heat absorbed and the heat released. This led to a profound realization. There's a physical limit to how much useful energy we can extract from the universe. Decades later, other scientists, including Lord Kelvin and Rudolf Clausius, would uncover what was hidden within that limit. Energy isn't lost. It spreads out. And as it spreads, it becomes less available to produce motion, order, or life. That's how the second law of thermodynamics was born, the law that governs every natural transformation. From that point on, physics was no longer just about forces and motion. It became the science of irreversibility and of time itself. What Sadi Carnot discovered was only the beginning. The real question was why heat always spreads and what that means on a larger scale. Years later, physicist Rudolf Clausius gave this phenomenon a name: entropy. He realized that whenever energy moves from one place to another, it tends to distribute itself, to occupy as much space as possible. It's not that energy disappears. It simply stops being concentrated enough to do anything useful. Think of a cup of hot coffee. Its thermal energy is concentrated in the liquid's molecules. Over time, that energy spreads into the air, the table, the walls, and the coffee cools. The total amount of energy remains the same, but now it's so dispersed that it can no longer be harnessed. That's the essence of entropy. The transformation of concentrated, useful energy into scattered, irreversible energy. It's why no engine can ever be perfectly efficient, why perpetual motion machines can't exist, and why every natural process involves loss. Entropy is the price the universe pays to keep transforming. And it's everywhere, in every chemical reaction, in every living cell, in every heartbeat. Each human breath is a small, temporary victory over chaos. We turn organized energy into heat and movement, but always at the cost of increasing disorder around us. When we look at the world through the lens of entropy, we notice something almost poetic. Life is a brief moment of order in a universe slowly spreading itself thin. If entropy makes everything spread out, if everything tends toward disorder, how can living beings exist? How does life create order, structure, and complexity in a universe that's constantly falling apart? The answer begins with a simple realization. Earth isn't a closed system. It's constantly receiving a steady flow of concentrated, organized, high-potential energy from the sun. Solar radiation reaches us as low-entropy light, energy that's highly concentrated. Here on Earth, that energy is absorbed, transformed, used, and then returned to space as high-entropy heat, more diffuse, less usable. That difference is what fuels life itself. Plants capture organized photons and turn them into living matter. Animals consume that matter and convert it into movement, heat, and thought. And each of these processes increases entropy in the surroundings, spreading even more energy outward. It's a constant cycle. Life consumes order and gives back disorder. But the most fascinating part is that this isn't a flaw. It's the very function of life in the universe, to accelerate the flow of entropy. Physicist Jeremy England proposed that whenever there's a constant energy source, like sunlight, and matter capable of absorbing it, energy-dissipating structures naturally emerge. In other words, life is a natural consequence of the second law of thermodynamics. Everything that lives, from a single cell to an entire forest, is, in a way, a machine for dispersing energy. Organisms organize themselves not in spite of entropy, but because of it. Life is not the opposite of chaos. It's the way the universe found to spread energy even more efficiently. If entropy is always increasing, it means the entire universe is moving in one direction, from order to disorder, from concentration to dispersion. And that's precisely what gives rise to time. In physics, almost every law works the same whether time moves forward or backward. Gravity, planetary motion, electromagnetism, all of these are reversible. But there's one exception, the second law of thermodynamics. It only works one way. Heat flows from hot to cold. Eggs break, but never reassemble. Smoke spreads, but never returns to the match. That asymmetry is what creates the arrow of time. The past is the state in which energy was more concentrated, and the future is the state where it will be more dispersed. This transition from low to high entropy is what shapes our perception of time itself. We remember the past because information about it is still organized, but the future is still too chaotic to be known. Physicist Ludwig Boltzmann was the first to connect this to probability. For him, time moves forward because the improbable always becomes the probable. There are infinite ways for a system to be disordered and only a few for it to be organized. So naturally, the universe drifts toward what's most likely: chaos. But that tendency isn't a bad thing. It's what allows things to happen. If everything remained perfectly ordered, nothing would move. Nothing would change. Time would be a frozen line. The fact that we live in an uneven, unbalanced universe is what keeps it alive, and what keeps the cosmic clock ticking. If entropy is the inevitable tendency for everything to spread out, then the entire universe is heading toward a point of no return. One day, all usable energy will have dissipated. No sun will shine. No atom will vibrate. No process will create a difference between hot and cold. It will be absolute equilibrium. And with it, the end of everything that changes. This scenario is known as the heat death of the universe. It's not an explosion, nor a collapse. It's the opposite, the universe slowly fading away as energy becomes evenly distributed, and time itself loses meaning. But before that end arrives, entropy still has much work to do. It has shaped stars and galaxies. It has given rise to life and consciousness. And it has also created the most extreme monsters in the cosmos: black holes. These are the most efficient entropy machines in existence. Every time a black hole swallows matter or light, its entropy increases. And when Stephen Hawking showed that black holes have a temperature, and therefore emit radiation, he confirmed that even they obey the second law of thermodynamics. Paradoxically, almost all the universe's entropy today is concentrated inside black holes. They are the great archives of chaos. And when the last one finally evaporates, something that will happen after a time span, written as a 1 followed by 100 zeros, the universe will reach its final state: a dark ocean of cold particles and low-energy photons with no structure, no movement, no direction. At that point, there will be no difference between past and future. The arrow of time will have vanished. And yet, there's something profoundly human about contemplating that fate. Because even knowing that everything drifts towards silence, it's in the middle of that process between the beginning and the end that the universe is at its most vibrant, most creative, and most alive. In the end, entropy isn't just a law of physics. It's the entire story of the universe told in a single direction. From the heat that drives a locomotive to the light of a star, from the photosynthesis in a leaf to the thoughts of a human mind. Everything that exists is in some way energy spreading out. But the most curious thing is that within that spreading, order emerges. Between an unimaginably simple beginning and an utterly uniform end, there's a brief, improbable, and dazzling interval where complexity blooms. It's in that in-between moment that stars are born, planets take shape, and life learns to reflect on its own destiny. Entropy may be the path toward the end of everything, but it's also what made everything possible. As long as energy still pulses and time still flows, every second is a living improbability, a fleeting resistance against the final equilibrium. And maybe that's what it truly means to exist, to be the instant between the chaos that was and the silence yet to come.